All right. Hello, everyone. Thanks for coming. Welcome to GraphBLAS, building a C Matrix API for graph algorithms. My name is Ben Brock. I'm a PhD candidate at Berkeley, and I work on large-scale distributed systems.
And I'm Scott McMillan from the Software Engineering Institute at CMU, and I've been working with graphs for about 20 years now, C++ for about 30. And going to talk a little bit about the C++ graph libraries that we've been working on for the GraphBLAS community.
Cool. Scott's going to start us out, and I will be back.
So, I work for a federally funded research and development center, so I have to show this information. Basically, if anything's wrong, blame me, not them. So what this talk is about, how and why to use matrix algebra for graphs, try to answer that question, and discuss what are some of the important data structures and concepts. I'll be covering the background, be mostly math, very little code. And then we'll shift over to more software, and Ben's going to come up and start talking about what the GraphBLAS community is today, and primarily talk about the C API that's been developed for the last 4 years. Then he'll transition into an overview of the draft C++ API that we're working on right now, and how this might interoperate with standard C++, and also the graph library proposal that's in the works. What this talk is not is a C++ standards proposal. So this is something different than that. And it is not a complete evaluation of graph programming models. We are specifically going to give it in the context of GraphBLAS, and we'll explain what that looks like. So how and why to use matrix algebra for graphs? For those of you who don't know what a graph is, it's basically a set of nodes or vertices connected by edges to represent relationships or whatever. Mathematically, it is two sets, a set of indices, often integers, and then a set of ordered pairs for the edges. So in a directed graph, the first index is the source of the edge, the second index is the destination of the edge. And you can see here, we have one edge going from 6 to 3 in green. It's represented by the ordered pair 6, 3. Graphs are everywhere. Ben and I are working in large-scale graph processing that finds applications in areas of social network analysis, cybersecurity, and biology, especially genomics and brain structure. Now, GraphBLAS is about graphs in the language of linear algebra. So graphs are represented by adjacency matrices. So this is the same graph again. And the information for the vertices are basically the set of rows that you have, the set of columns that you have, and the information on edges are entries that are stored in the graph. And so the same edge going from 6 to 3 is highlighted in green on the left and is represented by some stored value, and I'm not really going to specify what that is. That's the green dot at position 6, 3 in the matrix. Where we don't have edges, we don't store anything. And we'll go into a little bit about that later. So a little bit about GraphBLAS. So graphs in the language of linear algebra has been around since at least the 50s, I think maybe a couple of decades earlier. But in 2011, the state of the art of the community was collected and published in an edited book called Graph Algorithms in the language of linear algebra. Following on that, about 2 years later, was a decision by a large number of the researchers in the community that it was time to specify what the primitive operations were that could be composed to build a large number of graph algorithms using matrices and matrix operations. That was in 2013. Skip ahead to about 2016, and the community had published a paper on what it thought the set of a dozen or so operations were. That's the mathematical foundations, done in 2016. The first C API specification was published in 2017, and then a bunch of updates have happened since then, with a major update that will be released next month at Supercomputing. At the same time, we've had a number of implementations occur. The most popular one right now is Sparse GraphBLAS by Tim Davis at Texas A&M. And he's been doing a number of releases in the yellow across the timeline. Or blue, sorry, his is blue. So why do we want to do this? Well, we're patterning ourselves after the BLAS. So that's a basic linear algebra subprograms. It's a very popular API in the dense linear algebra community. It defined basically an API for these operations, and it separates the concerns between those who want to write algorithms and don't want to worry about the hardware, and those who know about the hardware and only need to implement a finite set of operations that then the algorithm writers can use. That was done in the 70s with updates in the 80s and 90s for the sets of operations. We're worried about sparse matrices, and there was a sparse BLAS extension to BLAS done about 20 years ago, but there was very little uptake. It wasn't really graph focused the way GraphBLAS is now. And so in 2013, we started the work on defining the API that specifically supports graph algorithms, can separate the concerns between those who need to work on how to get sparse low-level operations to work well on hardware, and the mathematicians or the analysts who want to write applications on top of the API. So getting back to graphs as matrices, back to the same graph for the example. One of the most pervasive operations is finding neighbors. Most graph algorithms are concerned with traversal across a graph. And so in this graphic here, if you look at a column of an adjacency matrix, it will highlight the edges that go into nodes. And so a column of a matrix can give you the vertices that have edges that go to a particular node of interest. Those are called the in edges. What's more useful, though, are the out edges. Generally, in a graph algorithm, you're at a node or a set of nodes. You want to know where you can go to next. And so the row of an adjacency matrix shows you what edges you can traverse to get to neighboring nodes, and those are the out edges. So this is by far the most important primitive in GraphBLAS. Now, how do we do that in an operation? We want to use matrix vector multiply. And so if we want to know the neighbors that we can reach from, say, node 3, we create a sparse vector. We set the location 3 with a some value, and we want to do matrix vector multiplication. If we did matrix vector multiplication with just the adjacency matrix, we would get all the nodes that feed into 3. What we want to do is take the transpose of the matrix and get all the nodes that we can reach by going out from 3. And so we do a lot of stuff with the transpose of the adjacency matrix. I like to organize it a little bit differently for reasons that you'll see in a minute. So I'm just going to move the vector that I'm multiplying by the matrix up. And so any element that's stored in that F vector picks off columns. The contents of those columns percolate to the right. And if there's overlap in the rows, they get reduced into the output vector there. I'm using circle plus and circle times there. And so, what is that? To explain this, let's go back to basic linear algebra that you would learn in school. You have y equals a times x. Y and x are vectors. A is a matrix. And what that really means is you're going to take the elements of the x vector and multiply it by the elements of the row of A, and then sum up all those rows. And so the implication is you're using arithmetic times and arithmetic plus to perform this operation. What GraphBLAS wants to do, and what makes it different than previous attempts, was that it uses semirings. And so a semiring is basically a more generalized version of the operations needed to do matrix multiplication. And so we can substitute binary operators for addition and multiplication and get a much richer set of computation just from the matrix vector operation in GraphBLAS. So this is a cornerstone of GraphBLAS and what makes it a bit different than prior sparse BLAS. And so just a little bit more about the semiring. the addition or the circle plus is a commutative binary operator that has a known identity, which we call the zero. Some people call this a monoid. It's actually technically a commutative monoid. I'm not going to get into the abstract algebra. I'm a software engineer. And then the circle times is a binary operator. And if you want nice mathematical properties, the identity, the zero of the plus, needs to annihilate in multiplication. So identity means a plus the zero gives you a back. And annihilation means a times the zero gives you zero back. And there are a number of useful semirings in the GraphBLAS community. We've talked about integer and real arithmetic. That's normal, traditional linear algebra that you learn. We use a lot of Boolean semirings, so trues and falses are stored in the matrices and vectors. We do and or. And then things like min plus, the tropical semiring is used in things like shortest path algorithms. So GraphBLAS consists of a couple of objects, sparse matrices, maybe dense. We don't really actually say what it needs to be. We leave the backend implementation up to the library writer. And we define a bunch of algebraic operators like semirings and monoids. And we define only about a dozen operations. And those operations, Ben may refer to them as algorithms later, consist of matrix-matrix multiplication, matrix vector, element-wise operations, a whole set of things that you would expect in linear algebra, and then a couple that you would find in graphs, like sparse matrix extraction and assignment. That's like subgraph extraction, subgraph manipulation. There's one more thing in GraphBLAS that I need to present before I go into how this is used to do something like breadth-first traversal, and that is masks. So every operation or primitive algorithm in the API allows the user to specify a right mask. This is analogous to, in the course of an algorithm, we may not be interested in an answer for a particular vector or vertex. And so you can specify a mask, we use the angle brackets M here, that can prevent writing to certain elements of the output vectors. And so we have the same matrix vector multiplication that I showed earlier. I have a mask that's going to prevent write in the first one. So say I'm not interested in going back to node 0 anymore. It will actually prevent creation of a result for that location in the result vector. The information in the mask can be used in implementations to reduce the amount of computation, make the operations much more efficient. That's just the notation that we use. So this is the mathematical notation for masked sparse matrix vector multiplying GraphBLAS. You have the matrix, the semiring, and the F vector on the right. You have the right mask on the left. You think of it as like a filter for what you're able to write in the output. And so with all of that information, let's just show you how breadth-first search works. So in breadth-first search, we want to start with a root node, and we want to find out how many hops it takes to get to all the other nodes that are reachable. And so we assign the F vector, we call it the frontier vector. That's the current active node, the source location in it. And we record its level, and we do that with arithmetic. So it's a scalar level times a vector F, and you accumulate it into what we're going to call the visited vector there. So visited is going to collect the answer that we want. So root node gets a 0. We build a mask from the visited list, so we're not interested in visiting node 0 anymore. We already have the information we need. And then we do the matrix vector multiply. So it finds nodes 1 and 3, it passes through the mask, and is written into the output vector there. Then it becomes the new frontier for the next iteration. So that's the finish of the first iteration. The second iteration goes basically the same way. I'm showing all the steps here. The nodes set in the frontier are multiplied by the new level, 1, and accumulated in the visited. The visited becomes the new mask. Matrix vector multiplication happens, and it finds 4 edges that it can traverse. One of them's trying to go back to 0. It gets masked out. The other 3 make it to the new frontier. That's level 1. Level 2 is pretty much the same thing. The visited list is getting full. A lot of things get masked out. In this case, we have two edges that find the same node, node 5. This is when the semirings plus operator comes in and combines the 2 values to write what you put in the frontier. So our frontier has 1 node left, node 5. And in the 3rd level, does a matrix vector multiplication, doesn't produce any output, and actually an empty frontier vector is the terminating condition. And so in terms of the mathematics of GraphBLAS, it is a 6-line program. It's a while loop. We have an empty test for no values being stored in a vector. That's our while loop. We have some arithmetic in line 4. We have semiring matrix vector multiply. I generally use the Boolean semiring for something like this. So we store trues where there are edges in the adjacency matrix, and we store trues in the frontier where we have active nodes. And it just all works out. And with that, I'm going to turn it over to Ben, who's going to talk about the coding aspects.
All right. Great introduction. So we'll start off talking a little bit about work in the GraphBLAS community on the GraphBLAS C API, and then how that's influenced us when thinking about a C++ API for GraphBLAS. So like Scott introduced, GraphBLAS is all about providing these primitives that you can use to implement graph algorithms using sparse matrices. And it revolves around matrix multiply, a generalized form of matrix multiply. Now, the C API has existed for some time. And while the C API has a lot of advantages, for example, great portability, it's very easy to make bindings for another language, it has some quality of life issues. The first one of which has to do with types. So if you're familiar with the dense BLAS, you'll know that for each primitive, for each function, for example, gem, which is general dense matrix multiply, there will be a different version of the function defined for each type. So here we have sgem, and then we also have a dgem for dense floating point values, or for, double precision floating point values. GraphBLAS supports a wide variety of not only types, but also binary operators. And this results in something of a combinatorial explosion when it comes to the number of actual functions you have to define. So for example, when thinking about a single operator, right, this would be one of those plus or times that you use inside of a matrix multiply. The implementer has to define all of these different operators. And then when you combine each of those scalar operators with the different types that are being used, you end up with many, many combinations of different types. And that creates a lot of burden for the implementers who have to generally resort to automatic code generation, essentially re-implementing C++ in a way. One of the other things I want to mention is descriptors, which are an important part of the C API. Descriptors are used essentially as flags, right? It's an extra thing you pass into the function, and you can kind of arbitrarily add things. Generally, they're transformations on the inputs. So you're saying, this input that I've given you, for example, this A matrix that I'm multiplying by the B matrix, please interpret it as the transpose of itself. And this is roughly on board with how the dense BLAS does this as well. There are also some other issues. For example, user-defined types are limited. So you can imagine if you were to have a complex type, you can do that, right? You can have this trivially copyable type, meaning that its copy constructor can be implemented with memcopy. It's just storing an int and 2 ints inside of it, one for the real and one for the imaginary part. And this has some nice effects in terms of the API, but has some limits on the expressiveness of the types that you can use as scalar types. And there have already been cases where people want to use more complex types, such as a short list of elements. Also, when it comes to custom operators, which are allowed in the API, the way that these are implemented are with function pointers. So you have a function pointer that you pass into this API. You need to do this if you want to define a new operator with one of the built-in types, or anytime that you use a user-defined type. And this results in a function pointer being called inside performance critical loops, which depending on the way the library is written and the way things are linked, can have some bad performance effects. Okay, so we've covered a few of the basics of the C API. Let's talk about some of the advantages of C++. So this will be no surprise to everyone, right? C++ has a rich type system with user-defined types as first-class objects. They simply have to have support for the lifetime events that are needed inside the container. Things like copy construction, default construction, et cetera, have to be defined if they're needed. And then one of the other things that's really interesting is that we can create views, which provide essentially transformed views of an object, which can greatly simplify the APIs for algorithms, similar to the C++20 ranges API. Before I get into actually looking at concrete code, I want to make a quick disclaimer that we're still working on this and a lot of the details are being hashed out. There are currently two main draft implementations, Scott's, which is called GBTLs, and mine, which is called RGRI. Some of the things that I talk about may be implemented in my code, but not necessarily something we've totally agreed on yet. All right, so let's talk about the kinds of things that we need to create in order to provide support in C++ for implementing graph algorithms using sparse matrices. The first class of things are objects. So things like a matrix or a vector. These are containers. They contain values. And then we can use them as inputs into algorithms. The second class of things are specific interpretations or transformations of objects. For example, a view of an object. And then the next thing are a class of callables that include binary operations and also some promoted binary operations that have some guarantees, for example, an identity that are associated with them that we can use to implement optimizations. And then, of course, there are the actual algorithms or operations, as they're called in the GraphBLAS vocabulary, namely the generalized matrix multiply, which is the most important primitive, but also some element-wise operations. Okay, so let's get started talking about a matrix. So a matrix is a collection of stored values, and it has a few attributes. So a matrix has a shape, which is the number of rows and the number of columns, the dimension of the matrix. It has a size, which is the number of stored values that are stored inside the matrix. And then also we need the ability to basically to do two things, to access individual locations within this matrix, right? So we can pick out a location, say 8, 4 within the matrix and ask, is there an element stored there? If so, please give me an iterator to it. And we also need the ability to iterate over all the values. So we can have a for loop or some series of for loops where we iterate over this matrix. Now, one thing that's not included in this matrix is an implicit concept of zero. And this is very important because in GraphBLAS, the concept of zero is associated with the algorithm, or maybe more formally with the monoid that is being used, and not with the object itself. And the reason for this is very important. It's because if you have a matrix, which is used in a certain graph algorithm, and then you were to assume, I have 0 as an implicit 0, so I can insert some spurious zeros if I need to, and then you use it in a second algorithm, that algorithm may be using a different monoid that has a different definition of 0. So these spurious zeros that you introduced are now resulting in an incorrect computation. So this is something that's associated with the algorithm, not with the data. Okay. So next, when talking about some of the attributes of matrices, I want to talk quickly, compare and contrast with what you would get if you tried to implement a sparse matrix using an unordered map. So what are the attributes we have in unordered map that are interesting to us here? The first thing we have is a distinct set of keys, right? So we have here a bunch of strings, x, z, y, b, which are stored in this data structure, and each key has associated with it a value, right? So we decided x will have the value 120, and so forth. And what are the things we can do? Well, we can, just like with the matrix, we can ask, does this map have a key in it? And we can also iterate over this unsorted range of elements. However, there's one very specific thing that an ordered map has that I want to point out that may not be the case with a sparse matrix format when we're using a high performance format, a sparse matrix format. And that is that the unordered map has a guarantee that the key type is going to be a pair-like type filled with integral values if we're using it in a sparse matrix type way, right? So now we've transformed these strings into tuple-like types. So you can imagine these are indices into the matrix, and we're indexing into these, and we have values associated with them. The matrix shape is going to provide some restriction for these key values. And that's fine, we can implement that. But what is an important restriction is that the implementation is going to be using highly specialized sparse matrix formats, which may involve compression. Now, what does compression mean for us? It means that these actual values that are stored, these keys, may not be present in materialized memory. That's kind of the point of matrix compression, right? We can elide some of the indices by using, for example, a compressed sparse row format, where we don't store the row indices directly. However, if we were to look at the guarantees that an ordered map gives us, let's suppose that we have this kind of sparse matrix-like unordered map that we've defined. It has a key type, which is a pair of integers that represent an index. And then it has a map type, which is the type of thing that is stored in the map. And then we were to request an iterator to that type. Now, what happens if we dereference that iterator? What is the thing that it gives us? So the things that it gives us is a C++ reference, right? A T ampersand reference to the value type. Now, what is the value type? Well, the value type is the thing that's stored in the matrix, right? The value including both the key and the mapped thing, right? The stored value. Now, the key is constant, right? So we can't just willy-nilly take an iterator and then modify the indices, which is a desirable property, but we can get a raw reference to it. And what this implies is that somewhere in memory, there is a physical memory layout where we have a pair of integers that are storing the indices, and then we have attached to that the actual stored value. So more precisely, we can say, oh, please give me a value type reference to this particular stored value. I can say, please give me the const pair reference that stores the indices, and I can also say, please give me an int reference to the stored value in the matrix. Now, when we move into the sparse matrix world, we'll see that actually we may not be storing all of the stored indices. So for example, here you can see on the right-hand side a compressed sparse row format storage. And so on the bottom, we have the sparse matrix representation, which is the sparse matrix that is logically stored. It has a shape, and then it has some indices that are stored inside of it. But when we look at the compressed sparse row format, we can see that all of the values exist, and indeed all of the column indices exist in memory, but the row indices are stored implicitly using these row pointers. So they're inferred based on your traversal of the data structure. And this is going to mean that we have to use custom reference types for indices. For example, if you're familiar with std vector bool, the majority of the STL data structures will require that the reference type is the actual, like a raw reference to the thing. But for std vector bool, for performance, it can be this custom type that will do the bit ops for you, that kind of logically references that particular bit. So we're going to be looking at a similar kind of reference. Sure. Yeah, so the question was, is there any particular reason to use the pair rather than a struct? So one of the nice things about a pair is that you can do destructuring on it, which is a very nice syntax. We actually don't actually store strictly a pair, but it's rather a pair-like struct. So yeah, that's a good question. Okay, so let's move on to a little bit of code to talk about what actually the API for the data structure might look like. So here we have a matrix. right? And the matrix has some template types. So first of all, we can specify the type of values you want to store inside the matrix. That's the type of the actual stored data. And then also we can ask for the indices, if the indices are being stored, to be stored using a particular integer type. This can be nice because if we have a smaller matrix and we know that we're only going to be storing indices in a particular range, we can use a smaller size for the indices, and this saves us on memory. Like we discussed, we can define a shape for the matrix, right? So we can declare a matrix that's going to be 1024 by 1024, and then we can go and ask what is the shape, what is the size of that matrix, i.e. what is the number of stored values that we have. We can ask if it's empty, all that good stuff. We can also ask for element access. And this element access, I'll remind you, depending on the type that is actually stored in the matrix, may or may not be a raw C++ reference. It could be something that is referencing, for example, a bool value that is stored in a bit representation. Similarly, we can ask to find a particular element and get an iterator to it and do comparisons, things like that, which are pretty standard for C++ data structures. When it comes to iteration, we also have a one-dimensional iteration concept. So we can iterate over this range of values, and then we can dereference these values in various ways. You can get a reference type, right? And then you can retrieve the stored values in the indices in a number of different ways. Right now, you can actually do it through implicit conversion, which is what you see here with the float x equals star iter. There's some debate about whether that should be left in. It is convenient. But you can also use this nice destructuring syntax where you say, I would like to iterate over this range. Please give me the indices, so I, the row index, j, the column index, and the value associated with that, and then we can manipulate those. Oh, and you can also use C++ data structure, C++ standard algorithms on these ranges. So I want to make a quick point about iteration and where things stand right now. So there are a lot of different potential sparse matrix formats that are useful. A few of them are on this slide. And each of them might have a different iteration pattern. So for example, if you have a CSR data structure, it is very efficient to iterate over the rows. If you have a CSC data structure, it is more efficient to iterate over the columns. And so that might impact what iteration order you want to use. It's inefficient to enforce a particular iteration order in general. And so right now, at least, we don't enforce one. So we have this unordered one-dimensional iteration concept similar to unordered map. And some of the ways that you can hint to the runtime that you would like a particular data or underlying data format, which may or may not correspond to a particular iteration order, is using a system of compile time hints. Okay, and like we mentioned, we're going to have this unordered iteration over the stored values. This is a range of matrix entry items, which is this tuple-like type, and then we can use that to manipulate the indices. Generally, you can get a T ampersand reference to the things that are actually stored, the stored values. Okay, next I want to talk about callables, which are an important class of, basically, we call them operators in GraphBLAS parlance, which are used inside the algorithms for scalar computation. So first of all, we have binary operators, which are functions that, like they sound, they accept two inputs, and then they produce a single output. So given operands that we want to put into this operator, and then a return type that we want to assign to it, we can define, okay, we have this binary operator, and it is callable with t cross u, the arguments that we're passing in, to v. So we can kind of define arbitrary operators. Here we're defining a lambda, and then pass those into a variety of different algorithms. Monoids are kind of an elevated form of mathematical or of binary operators. And so they consist of the combination of three different things, at least in GraphBLAS. You know, monoids are a larger topic, and there are different kinds, but here I'm talking strictly about GraphBLAS monoids in the GraphBLAS math spec. So they consist of a commutative binary operator, a type, which we call T, and then a mathematical identity, which is valid on that type. So given a binary operator, let's call it function, and a type T, we can ask this question, does this binary operator form a monoid when you use it on type T? This is basically saying, is this binary operator a commutative and associative operator with an identity when we use it on this particular type? And the way we do this is with this monoid traits specialization, which we define for a series of different operators, including both the arithmetic functions defined in std functional and also our own set of functions. So we could ask, given std plus and int, what is the identity there? Obviously, plus has a pretty boring identity, 0, but there are a variety of different algorithms that have interesting identities. So for here, we can retrieve this identity, and then we would expect 0 to be printed out, because 0 is indeed the integer 0 is indeed the identity for the monoid std plus on int. Let's see, so there are a number of different ways you can get monoids, one of which is using the predefined operators, both the std arithmetic operators and also slightly modified ones that we define. The user is also free to define their own specializations of monoid traits, right? If you have some type, you don't want to modify that type, you can go and define the monoid traits template struct to elevate it to a monoid with a particular set of types. And then you can have this guarantee that inside certain algorithms, you'll get the benefit of knowing that it's a monoid. You can also define your own type and then add an identity method into that type that'll get automatically recognized. And you can call this make monoid helper function, which will promote something into a monoid. Another important thing is semirings. So semirings combine a binary op with a monoid, where the binary operator distributes over the monoid. This is, for example, the classical addition and multiplication in classical linear algebra. But of course, you can define a bunch of other kinds of monoids. We predefine, or sorry, a bunch of other semirings. We predefine a number of different semirings, and users can also build their own semirings for either custom types or for other operators they want to come up with. So here we're defining a lambda and or two different lambdas, one for a times operator, one for a plus operator, and then we're creating this monoid so that we have a monoid and a binary operator to create in this semiring. Okay, so the next thing I want to talk about is this last class of things called views. I also call them interpretations of certain objects. So views provide typically a transformed view of a matrix. This is analogous to a transform view in the ranges API. So we can create views that represent, for example, transpose, structure, which is and complement, which are important views of matrices that I'll talk about later in the GraphBLAS algorithms. And these can greatly simplify the API. So you can see here, we're defining a matrix that we get from some place. And then we transpose this matrix, or we call transpose to get a transpose view of that matrix. And then we can pass that into a multiply function that will multiply A by its transpose without ever creating the A transpose matrix, without ever materializing it. So transform views, or matrix transform views, are a very powerful form of view where you can provide a transformation function to a view and then apply that function to every non-zero or every stored value that is present in that matrix. So for example, here we have an operator, a unary operator that just returns true for every single matrix entry. And we can create a transform view given a matrix and that binary operator. And this will have the same non-zero pattern and the same size and everything as the original matrix, but it will have true stored for all of its values, or it will appear to have true stored for all of its values in this view. So for example, if we had this matrix here, and then we created this transform view of it, it would have true in all of these locations. This is very important when it comes to masks, when you want to mask out any location that you have a stored value, even if one of the values might be 0, for example, or might be something that evaluates to false. So Scott introduced masks a bit. I'll just quickly cover this. So here we have a matrix that we're multiplying by a vector, and then we get a series of values out of it. If we apply an output mask to this operation, then some of the values will be masked out. So instead of getting 10, 5, and then 3 in the very last value, now we get 10 and 5. And 3 is masked out because we had 0 in that location. Masks are a specific interpretation of a matrix. So a mask is a range of matrix elements that have element-wise access methods, just like matrices do. They have a shape, but they also have the stored values convertible to bool. And if there's a stored value located in a location and it converts to true, that means that the value is not masked out. And that's an important primitive in the graph algorithms that we can implement with views. Okay, so let's talk a little bit about algorithms and then about how some of the concepts that we're working on defining for the specific data types that we pass into these algorithms. So the primary algorithms of interest are generalized matrix multiplication, which allows us to use a mask and to use an arbitrary semiring, and also some element-wise operations. So here we can see what a matrix multiply would look like. A matrix multiply takes in a series of matrices. Here we're doing a matrix multiplication of the matrix A multiplied by B, and then we're storing that result in C. You can also, as you can see, pass in a mask. Here we're passing in the view no mask, which will return true for every single value, and also the plus multiply semiring from classical linear algebra. And then you can also pass in an accumulator, which controls how the values that are computed are accumulated into the final matrix. Right. But these input matrices could also be views. They don't necessarily have to be GRB matrix types. So let's go through and look at some of the concepts. So the C matrix has to be what we call a matrix range, which is an output range of matrix elements that allow element access and allow the shape. So you have non-const access to each of the elements in this matrix. This either has to be a GRB matrix type or a writable view. The next are the input matrices A and B, which are what we call const matrix ranges. These are input ranges. You can't necessarily write to them, but you need to be able to read the elements in order to do the matrix multiply operation. Not sure what that was. And then finally we have a mask matrix range, M, which is defined to be basically the mask concept that we just talked about. It's everything that a const matrix range can do, plus the values are convertible to bool. Okay, so just before we finish up, I'm going to talk a little bit about interoperability with C++ algorithms. So the matrices that we've defined are ranges, which is nice, which means we can use them inside standard algorithms. I think an interesting area for exploration is actually implementing all of the operations, that is all of the algorithms using standard C++ algorithms. That's not something that we've done yet, but I think it would be really interesting to use parallel or C++ standard parallelism to get parallel implementations of all of these as well, just out of C++. The one-dimensional iteration concept that we have defined is somewhat limited. And so we've also been talking to people in the community about two-dimensional iteration concepts that people are working on for matrices. And one specific example of this is the C++ graph library proposal. which provides standard concepts for iterating over graphs and for implementing graph algorithms using explicit graph data structures. And while we aren't currently using multidimensional iteration, I think there's some really interesting opportunities to explore how matrices and the standard graph concepts could interoperate. For example, by having adapters that allow our matrices to be used inside graph library algorithms, or vice versa, or implementing our algorithms in terms of graph library concepts. Okay, so it's time to wrap up. So hopefully we've learned a little bit today about how we can use matrix algebra to implement graph algorithms and to support a variety of different sparse matrix formats while providing a high-level interface. There are some links in the upper right-hand corner to the various GraphBLAS resources, including the main GraphBLAS library, to the whole effort, and also to the implementations that Scott and I are working on. I also want to make a plug for my talk tomorrow, which is on a somewhat similar topic, basically building distributed data structures that use kind of custom iterator and reference types to provide support for things like hash tables and matrix types like this in distributed memory. And one of the things we're doing that I haven't talked about is actually trying to implement these GraphBLAS algorithms in a distributed version as well. Yeah. So with that, yeah, I think we have some time for some questions. Oh, yeah, sorry, go ahead.
So can you share some use cases of the GraphBLAS? Because I know for many of the graph algorithm, one of the fundamental concepts you want to use it because of irregular computational pattern. Right now, they are essentially trying to squeeze these irregular computational pattern to the matrix form. Does that give me some sort of freedom from or flexibility from using graph algorithms?
Yeah, so I'll repeat the question. It was broadly about what are the advantages of using a matrix-based formulation? What are some specific examples of why it's useful to implement graph algorithms using linear algebra? And I'll take a quick stab at it, and then Scott will probably have some comments. So the first thing that I would cite as an advantage, I don't know if this is a specific example, but an advantage of using sparse linear algebra is that you can take advantage of all of the prior decades of experience optimizing sparse linear algebra for graph algorithms. So all of the work on communication avoiding algorithms, both within a particular, like a single node and in distributed memory, you can use that work to get good performance for graph algorithms now, which is an advantage. I think one of the other advantages is, at least I would argue, programmability, right? So once you have this, single interface, you can implement, a wide variety of graph algorithms, and you have, instead of having like custom data structures, you have these, more general matrix types that you can manipulate. Yeah, I don't know if you want to add to that.
Well, there's a whole community that debate whether or not linear algebra is the right thing for graphs, but going back to Ben's statement, you can leverage decades of research in sparse linear algebra operations if you use this. And to answer the concerns of the graph community that want to think like a vertex, there is a large community effort to collect the algorithms, so lift the API even above the GraphBLAS API to say the LA graph algorithms library. And so that's an active area of development right now. And that's being used in the Python community to provide, even one step further away from, the hardware optimizations that you would have to do if you were thinking like a vertex.
Yeah. Yeah, if I could add one thing on top of that, I think another valuable thing is you only have to optimize a small handful of things, right? and then you can implement a wide variety of graph algorithms, as opposed to trying to optimize every single graph algorithm you write. Instead, you optimize a handful of primitives.
You optimize 12 primitives, and then you get arguably tens or maybe 100 different algorithms, and that's growing. So are there any other questions?
We have a couple of questions from our online audience.
Sure.
The first question is, what's the difference between STD plus and PRG plus?
Difference between STD plus and GRB.
That's a great question. So that's something we're still debating, actually, I should say. So in my implementation, the difference between STD plus and GRB plus is that not all the arguments need to be the same, right? So you could have an STD plus where you have a type T and a type U, and then you return even a type V, just depending on what the semantics of the type are. Whereas with STD plus, it's bound to a particular type. So you have T cross T equals T. So if you pass in an int and a float, it's going to bind to STD plus int, and then you end up with an int coming out of it. Whereas in GRB plus, basically everything is templated by default, unless you provide some restrictions. Yeah.
Yeah, and we have one more question. Did you consider representation for both bidirectional and oriented graphs?
I didn't catch the
Yeah, I didn't catch the last word.
Did you consider representations for both bidirectional and oriented graphs?
Bidirectional and
Oriented.
oriented graphs. I'm not familiar with the term oriented graphs.
Yeah, I'm not familiar with oriented graphs either. I think I may be misunderstanding what you mean by bidirectional also, but
is bidirectional undirected versus directed graphs? Is that?
yeah. So I can talk a little bit about the basically the correspondence between the sparse matrix and the graph. So if you have a symmetric matrix, that corresponds to a undirected graph, right? And we haven't fully considered symmetric storage, although it is definitely something that we're thinking about.
So yeah, in the C++ graph proposal, not ours, there is one representation. If you want undirected edges, you have to store both directions. And so you have a symmetric. I hope that's true. Andrew Lumsdane will correct me if I got it wrong. Sure.
Yeah.
So, thank you for the talk again. Is there any roadmap to support incrementality, like changing the graph, because this is a very, very common operation. For example, if I did a node or inserting a node into the graph, and right now you formulate everything into the matrix. If you want to dynamically change the graph, then does that mean you need to somehow, keep reallocating the matrix to adapt to the change of the graph?
Yeah. So I'll repeat the question. Yeah. So the question was about, is there any thought to allowing incremental edits to the graph, right? So instead of having to, have a big bulk transfer, can you have incremental updates to the graph and then do that basically amortized? So you only do a big reformat when you really need to. I think Scott probably has something to say, but I'll add that there's a lot of work on this in the GraphBLAS community, specifically looking at things like update lists. So basically delayed updates to the graph or to the matrix. So basically when you use the bracket operator, or when you use or when you use insert to insert something into the matrix, that is essentially updating the graph in place as you modify the matrix. Whether or not that happens efficiently depends on the underlying data structure, and there's definitely a lot of work optimizing the underlying data structures. For example, one thing you can do that's very simple is to have a list of updates, and then only do some bulk update once that list grows to a certain extent. And that's roughly comparable to like the amortized inserts into a hash table, right? Where you only resize the hash table every so often. You can avoid resizing the sparse matrix data structure. There are also sparse matrix data structures which are specifically designed for incremental updates, right? So the updates are only for things like CSR, which are not.
And we're trying to stay away from specifying what the underlying data structure should be. In the C API community, they call these objects opaque. We don't know how they're stored, and so the implementer is free to do whatever they want. We're trying to give lip service to that kind of philosophy, so there is this ability to pick the right data structure for the applications. And I think we're about out. Oh, there's one more question in the back.
The question is, did you think about separating the actual matrix arguments A, B, C from algorithm parameterization? I think that could result in a cleaner interface.
Sorry, so the question was about, have we considered separating the matrix parameters from the other parameters to MXM? So yeah, I'm not sure I understand exactly what you're getting at, but yeah, we're considering other forms of MXM. So the MXM interface that we showed here is very much influenced by the C API, which is nice for people who are familiar with the C API and want to move on to C++, but is...
it's the cultural compatibility that Bjarne talked about this morning.
Yeah. So we're definitely looking at other formulations, yeah, of the algorithm. Okay. All right.
Thank you very much.
Thank you, everyone.